Hello, in this video I want to make a summary of important results as they relate to the rank. So let's consider a matrix equation AX equals B. So this is a system of equations. We've got M equations in N variables, and let's let R denote the rank of A. So there's three cases that can occur. So first of all, let's look at what will happen when the rank of A equals the number of variables in the system. All right, and let's draw a picture to see what that would look like. So we've got a system of equations. So we've got a1, 1, x1 plus an a1, 2, x2, and so forth. And we've got n variables, so we'll go all the way up to a1, n, xn, and that equals some constant b1. And then we've got a second equation, and so forth. And we'll go all the way down to our last equation, and we're told that we have m equations, so we'll go all the way down to am1 x1 plus an am2 x2, and so forth. And so what this turns into is an augmented matrix that looks like a1, 1 and an a1, 2, etc. And then we have our constants down this other column, and an a2, 1 and an a2, 2, etc. Down to our last row, which is the mth row. Oops, it should be an a sub mn. All right, so let's look at this. If the rank, so this is our matrix A, and if the rank of A turns out to be exactly equal to the number of columns, the number of variables, so if rank equals the number of variables, which is essentially the number of columns, this is called a full rank matrix. And what this shows is that no matter what we put in for our column vector, any column vector B, we will get a unique solution. Right? So when we RREF this, if we have a full rank matrix, what we're looking at is ones down this diagonal, and who knows what we get over here in this right hand column once we work out all our RREF business, but we do know that we'll get a unique solution to the system of equations. So that's one important result. The other thing we'll notice is that, this vector B could have been anything, could have been the zero vector. So if that B was a big zero vector, then our augmented matrix, once we RREF it, we'll get a full rank matrix again, but we have a bunch of zeros over here. And this tells us that the column vectors of A are linearly independent. One last observation here is that no matter what we put in for vector B, so no matter what B we pick, we always get a unique solution. In other words, what this says is if we look at the column vectors, let me write it this way. Write it with the X. I'm trying to find a different letter, so let's choose V. If we look at the column vectors, maybe we'll write them as column vectors this way. There we go. If we look at the column vectors of matrix A, we can see that they span all of our n. So let me write this down, and I'll try to stop talking and writing because that's a lot to write and a lot to say. So our last CN here was A1, N, A2N, all the way up to AMN. So we can build any vector. We can build any vector as a linear combination of the columns of A. And so this shows that any B that lives in Rm can be generated by the column vectors of A. And so we get this idea. For example, if we were in R3, we might get some of our vectors. Let's say here's our first vector, our first column vector of A, and here's another column vector of A, and here's maybe another column vector of A. The column vectors of A span, the column vectors of A span the entire space. Okay, and so no matter what B I pick, let's say there's a B, we could certainly generate that B because these column vectors of A span the entire space. Okay, let's take a look at the second scenario. So let's see, our first scenario at the very top here was if R equals N. Let's look at another scenario down here. This is case 2. This is if R is less than N, and we're going to have to break this up. There's going to be a case 2 and case 3 where they're both less than N. It's not a full rank matrix, so A is not a full rank matrix. And we need to differentiate kind of between this infinitely many solutions case and the no solutions case. So I'm going to add a little bit more on to this case in a moment. So here's our matrix A. If we RREF it, we will get down to a case where we get some ones, but eventually we don't get any more ones, and eventually we're just filled up with some rows of zeros. And here's our vector B, which has been somehow, we add scalar multiples and things like that to the rows during the process of RREFing. And so we need to look at what we get at this point, because if these last two little rows in this example were 0, we would get an infinitely many solutions case. And if these last two entries in that last column were not 0, we could get no solution. And so how to differentiate between those two? We will look at not only the rank of A, but we'll look at the rank of the entire augmented matrix. So that's how we will differentiate these two cases. All right, so let's say if the rank of A is less than the number of variables and the rank of the augmented matrix, so there's our coefficient matrix together with B. So if the rank of A is less than the number of variables and the rank of the augmented matrix is the same as the coefficient matrix, then we are certainly looking at this situation where if we looked at the entire augmented matrix, it's only, rank 3 in this case. If we looked at just the coefficient matrix, it's still the same rank. So when the matrix of coefficients and the augmented matrix have the same rank, we get infinitely many solutions. In this case, the column vectors of A do not span the space. And so it's not the case that you can generate every vector b. So let's just take a look at a picture here. You might have three little vectors and they live all down in maybe a plane. Right? So they live all down here in this plane. And if you come along with a vector b that lives down in that plane, that's great. You will get infinitely many solutions. But if you're looking at a case where that vector b does not live in the plane, you would get no solutions. So again, case 3 is this situation where the rank of A is less than the number of variables. We have A is not full rank. And in this case, we'll say that the rank of the augmented matrix is not equal to the rank of A. And so what this would look like, and so you get a bunch of ones down that main diagonal, and then you get some zeros in the bottom row. And here comes, and let's say these are non-zero over here, so let's put some number. I'll just put a 5 for the sake of an example. This gives us a no solution situation, and the picture that goes along with this is that we've got these column vectors of A living down in some space, maybe a plane, for example, in R3. And here we come along with a vector B, and B doesn't live in the span. So B does not live in the span of the column vectors of A, and that's why we can't generate it. We cannot write B as a linear combination of column vectors of A. So you could not find coefficients that would make this work, for example. So that's our no solution case. So again, 3 scenarios as they relate to our classic unique solution, infinitely many solutions, or no solution scenarios. And it all comes down to really looking at the rank of the coefficient matrix along with the rank of the augmented matrix. So there are 3 cases. We had the unique solution case where we had full rank matrix, and then we had case 2, we don't have a full rank matrix, but we do get infinitely many solutions, and then the case 3, we do not have a full rank matrix, and we get the no solution case.